Right, well, good morning, everyone. Thank you very much for the invitation to speak. It's a very great honour. Firstly, it's an honour, obviously, to speak in memory of Jan, and also to join the list of illustrious speakers. I feel a bit like an imposter, but I'll do my best. So I wanted to start with a photo. It's the only photo I have of Jan during my PhD. It was taken in the final year of my PhD. So Jan went to California to work with Bob Guralnick, and I joined him along with another of his students, Jonathan James, so one of my academic brothers. And we were there for a term. We were based at Caltech, and I was starting the process of writing up my thesis. And this photo is taken on top of Mount Baldy, which is a big old mountain that we walked up one day while we were there. And I kind of like this it's a nice photo, if you'll allow me to be a little sentimental, because mountain climbing and writing PhDs have many parallels. Blooming hard work to start with. You often can't see the top. When you get there, you hope you'll have a good view, but you might not, etc., etc. Perhaps the most pertinent parallel is you want a good guide. You don't want to be wandering around a mountain in the fog on your own without somebody there to help you. And of course, Jan was my guide for my PhD, and I'll be always grateful for the guidance that he gave. So yeah. Yeah, so that's a good point. Actually, no, I can't, is the short answer. The question. So Jan's on the right, obviously, I'm next to him. On the left is Jonathan James, who is one of my academic brothers. And then the other two people, I can't actually remember their names, because it's been a while. So if they're listening, I apologise. How's that? All right, so that's enough on that photo. And as Martin alluded to earlier, I'm representing really Jan's students, so I just wanted to note who they were. I hope this is an exhaustive list. I got it off the Mass Genealogy site. I don't know all of them. I've got one sister who's in the room, and I think there's at least one of my brothers is online, and possibly more. So anyway, and we all owe a great debt to Jan. So I wanted to just note people's names. There's another generation, maybe there's more than one generation, I don't know, not represented, but it's an impressive legacy to add to Jan's many achievements. All right, so I wanted to go on now to the maths. So halfway down there is David Rodgers, who I've never met, but the inspiration for what I'm going to talk about is a theorem that Jan and he published together, I think based on David Rodgers' PhD. So let me just give the context for this theorem. So it's about multiplying sets in groups. So you may well have thought about this sort of stuff yourself, but just indulge me, I'll just set up the notation. So I'm going to always think about G being a simple group of Lie type. It doesn't have to be, but for this purpose of this talk, that will do. If I've got a couple of subsets A and B in the group, I just define the product set in the obvious way. So the product of the sets A times B is just taking an element from A and an element from B, multiplying them together and looking at all of the possibilities. And then we want to ask questions about what this product set looks like. We might just ask it completely, sort of the most general question, A and B are arbitrary subsets. We may restrict to the situation when A and B are subgroups. An important case for me is when A and B are normal subsets of G. So you can probably guess the definition, just a generalization of a normal subgroup. It's just a set that's invariant under conjugation. Another way of saying it would be that a normal subset is a union of conjugacy classes of G. And as we shall see, this is going to be the sort of starting set that I'm going to consider. And what do I mean by what does this product set look like? Well, the standard sort of questions, there's two that I'm going to consider in this talk. So the first is how close the size of that product set is to the product of the sizes. So hopefully it's clear that the product of the sizes is as big as it could possibly get. If all those products up there were distinct, then your product set would be equal to the size of A times the size of B. But of course, usually there's some overlaps, and so it will be a bit smaller, and so you sort of compare those two quantities. And then the other question you might ask is under what conditions the product of those two sets is equal to the full group. Okay. And it's actually that one that I'll spend most of the time on. I'll come back to the first question a little bit right at the end if I have time. That's the setup. I've just expressed everything in terms of the product of two sets. Of course, you can extend it to as many sets as you like. So A, B, C, D, etc., etc. You can multiply them and ask the same sort of question. Okay, so that's my notation. So now I'm in a position to state the result that Jan and David Rodgers proved. So this was in 2003. So it's the following. Suppose that C1 up to CK are conjugacy classes in SLNQ, and suppose that the product of their sizes is at least the size of SLNQ to the 12th power. Then that's enough to guarantee that the product of the conjugacy classes is actually all of the group. Okay? So it's a lovely result. It's very explicit, nice number 12 there. And that's the inspiration for what I'm going to talk about now. I should say that a very important similar result had come out a couple of years earlier that's been used in many places. You're probably aware of it. Let me state that. So due to Liebeck and Shalev, there exists an absolute positive constant C such that if G is a finite simple group, S is a normal subset of G, and M is an integer satisfying this inequality that the size of S raised to the M is equal to the size of G raised to the C, then G is equal to that M products of S. It's not normally expressed quite in this way. There's normally some loggy things in there. But I'm really expressing it like this to have a parallel with Jan and David Rodgers' result. Wonderful. So just to compare the two, so the Liebeck-Shalev result obviously has the advantage that it holds for all finite simple groups. It also holds for normal subsets rather than conjugacy classes. It's like the advantage that the Jan and David Rodgers result has is that they specify the constants of the 12. And of course, they're dealing with a whole bunch of different conjugacy classes rather than just one normal subset multiplied by itself. It's maybe just worth noting that you have to be careful about the order that you do your conjugacy classes. So that it's, we're specifying C1 up to CK, and then we're multiplying them in order. And so changing the order potentially is going to change things. All right, nice one. So hopefully that's all clear. I should just say, so it should be clear that we need the size. So just looking at that second theorem there, if you're going to have any chance of G being S to the M, multiplying S M times and getting G, then you certainly need that the size of G is bounded above by the size of S to the M. Okay. So this theorem is sort of like a sort of converse of that. Like the bottom is a necessary condition, and then the theorem gives a sufficient one, and albeit just with the addition of this constant C. So it's a very powerful result. It's sort of saying that really, as soon as you're big enough, that's all you need. You'll get the full group when you multiply. Okay. Wonderful. So I guess the starting question I have in light of these results is to what extent you could, so both of these are about normal subsets, conjugacy classes or normal subsets. So the question you might ask is, well, to what extent would these results carry over to just arbitrary subsets? And your immediate answer would be, well, not at all. There's no chance of being able to prove that sort of result for an arbitrary subset. Just take, for instance, S to be a subgroup of your group. You multiply S by itself as many times as you like. You're not going anywhere. You're staying inside S. Okay, so in that sense, there's no way of generalizing this to an arbitrary subset. However, there is a way in which you can re-ask the question. So let me just explain what I mean by that. So instead of multiplying a set by itself, I want to talk about products of conjugates of sets. So here's the setup. So let's just take, again, two subsets of some group G. We might as well think of it as being a simple group of Lie type. And I've just defined what it means to take the conjugates. Hopefully that's totally obvious. So we conjugate A by some element G and B by some element H. And now I imagine, instead of just looking at A times B, I imagine looking at all the possible ways I could multiply a conjugate of A by a conjugate of B and see how big it could be. Okay? So I can ask the same questions as before in this context. So I could say, if I allow myself to range over all these conjugates and I just look at the biggest, what are my chances that that's as big as possible? So maybe A times B was kind of small, but if I allow myself to range over all the conjugates, maybe I'm going to get something big, maybe it's going to be close to that maximum possible size. And then likewise, the same question as earlier, when can I find conjugates that give the full group? Okay, so why am I talking about this? Well, the point is that if A or B is normal, then these are just the same questions as before, right? So if you've got a conjugacy class and you conjugate it, you don't go anywhere. So the results that I just seen, that I just showed you here, you could think of them, it'd be a bit contrived, but you could think of them as statements about products of conjugates of sets, okay? Albeit that in this context, taking conjugates doesn't actually help you, okay? But if you think about these questions in that context, then asking them about arbitrary sets then suddenly starts to make sense, because the subgroup counterexample is no longer a counterexample. It now makes sense to ask about what it means to multiply conjugates of subgroups. Okay, and so that was exactly the setting that inspired two results that I want to share with you. So these are analogues of those two theorems. So the first one was with those fellows there, Latzi Piba and Endre Sabot from the Renyi Institute, and Ian Short, my colleague at the Open University. And this appeared a little while ago. Here's the result that we proved. So fix a positive integer r. There exists a constant c which depends on that r, such that if G is a finite simple group of Lie type of rank r, S is a subset of G, and M is an integer satisfying that inequality, then G is a product of M conjugates of S. Okay. So that's the sort of analogue of the Liebeck-Shalev result, but taking products of conjugates. Of course, the big weakness is we have a dependency on the rank. So the Liebeck-Shalev result had an absolute constant, whereas this one has a rank-dependent function. And then a little bit later, with two of the same fellows, we proved the analogue of the Rodgers-Saxl result. So this says the following. So if we fix a positive integer r, then we can find a constant c depending on r, such that if G is a finite simple group of Lie type of rank r, and you've got these subsets satisfying, again, the same inequality, that you can find conjugates so that G is a product of all of them. Okay. So that's quite satisfying. So we've got these two interesting results about products of normal subsets, and it turns out that we can indeed think of them, generalize them to arbitrary subsets, provided we allow ourselves to take conjugates. I mean, that's good, but it's not really what we think is true. So I think in these papers we conjecture that actually we should be able to do better. We should be able to prove direct analogues of those same results. So basically, this is a restatement of the earlier one, but with an absolute constant. So we think that, and when I say we, I can't quite remember which conjecture appeared where, but it's in one of those two papers with those same geezers. Conjecture that there does exist an absolute constant C, such that if G is a finite simple group, and S1 up to Sk are arbitrary subsets of your group, satisfying that same inequality, they're just big enough, then you can express G as a product of conjugates. And that's a generalization of the product decomposition conjecture, which again is the analog, the sort of absolute constant analog of the theorem I put on the previous slide. Okay. So there we go. So that's what we believe to be true, but so far there hasn't been a huge amount of progress. The one thing that I can report is the following. So this is about what do we know with absolute constants in this setting. So a recent paper of Marotti and Pieber in 2021 proved this theorem. They proved, effectively they generalized the Rodgers-Saxl result to normal subsets of arbitrary finite simple groups. They didn't have the number 12, so that's a slight weakness. They do, however, talk about normal subsets rather than conjugacy classes. It's not actually, one question I had as I was sort of thinking about this, it's not totally clear to me that you can easily go from the original Rodgers-Saxl result about conjugacy classes to a statement about normal subsets. Possibly there's a neat trick that you can do that, but it was beyond me. Anyway, so this theorem does the job. So it says that there exists an absolute constancy. So you've got a finite simple group, you've got a bunch of normal subsets. They satisfy the inequality of the kind that we want. Then you do indeed get G as being a product of those fellows. So that's really good, but it doesn't. It's still in the regime where we're looking at normal subsets and conjugacy classes. So in terms of proving results with absolute constants for arbitrary subsets, we haven't got much. I haven't got much to show you, unfortunately. So please consider that a challenge. But maybe what I wanted to do was just briefly mention sort of how we went about proving the rank-dependent results, so that I can show you the weak points in that method. So possibly there's some inspiration in the room, and maybe we can get somewhere with absolute constants. So the big tool that we use, the big beast that helps us prove these results. So maybe the theorem I should focus on. Let me just go back. So if we just think about this top one. So this is just where you've got an arbitrary subset S inside your finite simple group of Lie type of rank R, and you just want to show that you can express G as a product of M conjugates of S where M is not too big. Okay. So let's think about proving that theorem there. So I'll come back. Where was I? Yeah, so this is the sort of main tool we use. It's called the Product Theorem, one of whose authors is sat in the front row. So Broyard, Green and Tao proved this, and then Pieber and Sabot proved it simultaneously. It's very, very celebrated and powerful result with millions of applications. This is just one. So I'll just remind you what it says. If you fix a positive integer r, then there exists an epsilon which depends on r. So if you've got a finite simple group of Lie type of rank r, and A is a generating set of G, then either 3 copies of A give you all of G, or 3 copies of A grow in size exponentially. Okay. An important thing to note is that we've got this epsilon depending on R, and it's known it has to. Okay, so there's no hope of proving a product theorem with an absolute constant. If you're just going to multiply sets by themselves, you have this rank dependency is built in. There's examples to show that you can't do better. So this is as good a theorem as you're going to get of this kind. So that's our tool. So how would we prove this theorem about multiplying sets by conjugates themselves? So the proof depends on the size of the set S. And I'm just going to wave my hands a bit. So for S large, you use the product theorem. Effectively, the point is you're allowing yourself to multiply S by conjugates of itself. But the product theorem just says, just use S itself. Just multiply S by itself, and that'll be just fine. That'll do the job for you. So, but S needs to be large if you're going to get the right bound. So that's easy. We didn't have to do any work there. For S small, what I've written there is be greedy. So it turns out that you can do a relatively elementary combinatorial argument, which says that if you've got a group G and a set S, if S is pretty small, then you can always find some conjugate of S such that multiplying the two will give you as big a growth as you could possibly get. Okay. So let me make this precise. The lemma we prove is this. So suppose that A and B are subsets of a finite group G. And suppose in addition that the size of A and B are bounded above by this fellow here. So min class is the size of the smallest non-trivial conjugacy class of G. Okay, so if you're in a finite simple group, that's fairly big, big enough anyway. It's big enough to be useful. So it's going to be bounded by that number raised to the quarter power. Then what it says is you can find a conjugate, so a b to the g, such that if you multiply them, you get as massive growth as you can possibly hope for. So you get the best possible growth. So the strategy, if to prove a theorem, is super easy. It's you take you start with your set. If your set's big enough, you just go, I'm just going to apply the product theorem, finished. If your set's not big enough, you go, all right, I'll use this cheeky lemma here, and I'll find some conjugates, and I'll just multiply them to get growth as big as possible until I get to a certain size. And fortunately, that size is just big enough that I can throw the product theorem at it, and job done. Piece of cake. So that is brilliant. All right. So that's how we prove the rank-dependent result. So how would you think about maybe proving an absolute constant result? Well, the point. So what we want to do is we're not allowed to use the product theorem because it's rank-dependent. So what's the thing that really stops this here? The greedy approach fails when A and B contain almost all of a conjugacy class. So somehow you multiply together, and things start, you don't, at some point you know you're going to not be able to get this maximum possible growth, and it turns out that what's happening is you sort of effectively start filling up a conjugacy class somehow. Okay. Well, to me that's kind of intriguing, because just imagine that you could actually go a bit further. So imagine you could find conjugate classes. You don't just almost fill the conjugacy class, but you could sort of extend this argument till you actually contained a conjugacy class, right? So just imagine that you could go a bit further. Then what you want to do, ideally, is you want to use the Liebeck-Shalev result right at the start, which gave you growth with an absolute constant, right? And so ideally, you'd replace the use of the product theorem. You'd multiply with your clever skills. You'd manage to get yourself a conjugacy class in there. And then, with any luck, you could just go, oh, look, I've got the Liebeck-Shalev big result. Fire that one in, the end. But there's this gap. You don't actually get all the conjugacy class. You just get almost all of it, or some big proportion of it. So therefore, I want to ask this illustrious group the following question. Because maybe I'm not saying this question bridges the gap, but it's a question that sort of is in the spirit of what I'd like to think about. So does there exist an epsilon greater than 0 with the following property? Possibly it's a stupid question, by the way, so forgive me. Maybe that you can easily sit there and say, nah, of course not. But anyway, I'll give it a shot. So suppose that you've got an A which lies inside a conjugacy class C and is nearly all of the conjugacy class. So in the sense that it's C to the 1 minus epsilon. Does there exist a conjugate of A, such if you multiply them together, you get yourself a conjugacy class? So you get from having almost all the conjugacy class to actually getting all of it. Or maybe, tell you what, I'll allow you to multiply it a few times. 3, 4, 5, I don't care how many conjugacy classes, just a bounded number of products that will get you a full conjugacy class. And then maybe there's a chance that you might be able to get somewhere. I'm aware that I'm just about running out of time, so I'll try and wrap it up very rapidly. So here's the message so far. So we believe that results on growth of normal subsets should extend to results on growth by conjugates of arbitrary subsets. So I hope I've given you examples of that. And what's more, we believe that these results on growth by conjugates of arbitrary subsets should yield absolute constants. When I say we believe, it's just I believe. But anyway, I'm putting it out there. In contrast, results on ordinary growth of arbitrary subsets are known to yield rank-dependent conjugates. Rank-dependent constants. So there's a definite difference in what's going on in those two regimes. And just to illustrate that, I'll just give you one final slide, which is sort of, I mentioned that other question, so I've been really asking about how to get the full group G. So I just want to give you another thing just as a sort of contrast. So here's the product theorem again, just to reprise that result. And I want to give you yet another conjecture, which sort of is like was in one of those papers with Pieber and Sabah, I think the one with Short as well, which proposes like a product by conjugates product theorem. So it says the following: there exists an epsilon greater than 0 and a positive integer b, such that if you've got any subset of a finite symbol group G, you can find a conjugate such that either that conjugate grows exponentially by this 1 plus epsilon, or G is the product of B conjugates of S. Okay. So this, hopefully you can see, this is basically the product theorem. The 3's in the product theorem have been changed to sort of a 2 and a B, but whatever, that's not the key difference. The key difference is we've got an absolute constant here, rather than a rank-dependent constant. So that would be kind of groovy. And just, I want to finish with one final conjecture, which is of a very different style, but I kind of like it just as a variation. Oh shoot! I'll see if I can move this. Oh, I've made it worse. Oh yeah. Oh, well done. Right, nice one. Yeah. Okay. Okay. So this is just by way of contrast. So, because I haven't really talked about what happens if you specify to subgroups. I've talked about sets and I've talked about normal subsets. So this is instead. Suppose instead I was going to talk about maximal subgroups.